This section will show how reinforcement learning problems are set up by exploring the Markov decision process with dynamic programming. We'll show how to frame reinforcement learning in the MDP framework, dive into dynamic programming, and detail important fundamental concepts like policy iteration and value functions. We'll start Section 2 by reviewing the MDP framework, rewards and policies. The Markov decision process framework is used to model most reinforcement learning problems. It's a mathematical framework to describe and help solve RL problems. The diagram on the slide shows a basic MDP. The circles with S in them are the states. Note the arrows that show which states may transition into each other, and R, which is the reward received. Let's discuss what it means to be Markov. The key idea in MDPs is the Markov property. The Markov property means that all needed history is stored in the current state, given the prior state. All history can be collapsed and stored into the prior state. If you know the prior state, you know all the necessary history. While that may not be strictly true in practice, it can serve as a close enough approximation to allow us to solve RL problems. The Markov property allows representations of sequential problems without having to rely on overwhelming amounts of historical data. This is useful for RL because RL often deals with sequential problems. More formally, the probability of state S at time t plus 1 given state S sub t is equal to the probability of st plus 1 given all prior state history. Next, we'll go over key MDP terminology. MDPs contain reward R, discount factor gamma, actions A, state transition probabilities PR, and state S. In the context of MDPs, the reward R is a scalar received by transitioning to a state. The return G is a sum of rewards discounted from the current time step t. The formula for G sub t is RT plus 1 plus gamma times RT plus 2 until the end of the return. Note how gamma is continually multiplied by itself. The discount factor gamma is applied to future rewards and state valuations. Gamma accounts for the uncertainty in the environment. Gamma also makes the math more convenient. Gamma is in the 0 to 1 range, with 0 meaning that future states/rewards are not accounted for, and 1 meaning that future states/rewards are weighted highly. Gamma less than 1 can be seen as a cutoff. For returns far enough into the future, gamma will effectively be 0, and no returns past that point will matter. This can help you when choosing what value of gamma to use for your problem. Consider, how much of the future do you want your agent to account for? The agent can select an action, which may result in remaining in the same state or transitioning to a new state. A policy pi is a collection of probabilities for each possible action. A state action value can be used to evaluate the goodness of an action given a state. MDPs define the transition probability PR of going to the next state, given the preceding state in action. The formula is read as the probability of ending up in state S prime and receiving reward R, given that the agent took action A in state S. Here's a simple example of the transition probabilities in a Markov process. There are 3 states: sunny, cloudy, and rainy. The arrows represent the allowed transitions, and the numbers the transition probabilities. For example, there is a 0.5 chance for a sunny day to remain a sunny day, a 0.3 chance for a sunny day to become a cloudy day, and a 0.2 chance for a sunny day to become a rainy day. Next, we'll add the rewards to the MDP. This is the same example, except rewards are included in the parentheses. For example, if you go from cloudy to rainy, the reward is 0. If you go from sunny to cloudy, the reward is -1. The final term we'll introduce this video is the Markov state. In a Markov state, all needed history is stored in the current state, given the prior state. Based on the rewards, actions, and transition probabilities of the states, we can assign values to states with a value function Vs. Q values, written as QSA, are the state action values, aka action values. Vs values the state. QSA values the action A taken in state S. Vs and QSA define the expected value of the state and state action combination. Vs and QSA are examples of value functions. Value functions are an important concept in RL. Value functions let agents assign a goodness value to states and state action combinations, which help agents determine which states to visit and actions to take. Value functions are based on the expected value of returns. We can extract policies from value functions, as we'll see in this section in Section 3's DeepQ network videos, or use value functions to help optimize policies, like we'll do in Section 4. Here's an example of the MDP framework with state values. The transition probability at each step is 1. It goes from A to B to C, and then stops at. Inside each circle is the name of the state, a letter, and the state value inside parentheses. The top example has gamma equal to 1. The bottom example has gamma equal to 0.5, so the reward from later states is heavily discounted. Note how much less the state value of A is when gamma is reduced.